pile of rubble. Given this brief time scale, there must exist a repository of cometary nuclei in the cold outer solar system from which the supply of short-period comets is replenished. One obvious repository is the Kuiper belt. This would explain why most of them have relatively small inclinations, which match the relatively small inclination of the majority of Kuiper belt objects. But how can we explain the short-period comets that are on retrograde orbits? To explain the origin of retrograde short-period comets, it helps to consider the origin of long-period comets. Long-period comets are defined as comets with a period of more than 200 years, and hence semi-major axis of more than 34 astronomical units. Some long-period comets have periods that are very long indeed, with a period of around 3 times 10 to the 7 years, implying a semi-major axis of 100,000 astronomical units. Long-period comets have other characteristics in common besides their long orbital periods. These are as follows. Long-period comets have random inclinations to the ecliptic, with as many being on retrograde orbits as on prograde orbits. Long-period comets have extremely high orbital eccentricities of around 1. Over 800 long-period comets have been detected over the course of history. The Dutch astronomer Jan Oort, with OORT being the name here, proposed that long-period comets reside in a large, roughly spherical cloud of radius around 50,000 astronomical units, centered on the sun. This distribution of cometary bodies is called the Oort cloud. The radius of the Oort cloud is not negligibly tiny compared to the distance of around 270,000 astronomical units to the sun's nearest neighboring star. The orbits of cometary bodies in the Oort cloud can be perturbed by passing stars. This alters their orbits and sometimes permits them to approach the inner solar system. Those few objects with perihelion distances of less than 4 astronomical units grow commas and tails and can be observed by us as comets. Retrograde short-period comets, such as Comet Halley, represent long-period comets that have had a close encounter with the Jovian planet that has flung them onto a smaller orbit. So close encounter with the Jovian planet might fling them onto a smaller orbit. The chemical composition of cometary nuclei indicates that they were probably formed about 20 to 30 astronomical units from the sun between the orbits of Uranus and Neptune, where the temperature of the pre-solar nebula was around 100 kelvins. So remember the temperature on Pluto was around 51 kelvins at aphelion, so that gives you some idea. If they had formed closer to the sun, they would not have been icy. If they had formed farther away from the sun, their water would have been locked up in solid hydrates of ammonia and methane. Thank you for liking the live. Thank you for joining the live. Can we please like the live? Can we get 30 likes? Since water vapor is detected in the spectra of comets, so we see water vapor in the spectra of these comets, this clearly did not happen. The orbits of these small cometary bodies were easily altered by encounters with the massive Jovian planets. So they could not have been made in that particular distance, because we see if they had formed farther from the sun, their water would have been locked up in solid hydrates of ammonia and methane. Since water vapor is detected in the spectra of comets, this clearly did not happen. So the orbits of these small cometary bodies were easily altered by encounters with the massive Jovian planets. If their orbits were not altered, it would be different. Thus, they were scattered onto a wide variety of different orbits. So they may have started somewhere and formed somewhere, but they were scattered about with a variety of ultimate fates. So depending on which comet you are, you may have a different fate. As follows: comets on small orbits made Frequent perihelion passages and sublimed early